Everyone, welcome back. This is lecture 10 of the lecture series Signals and Systems. So in this video, we will be discussing about the properties of continuous time Fourier transform. And as important cases, we will see the convolution property and the multiplication property. And we'll see the basic Fourier transform pairs. And finally, we'll see the frequency response of LTI systems represented by linear constant coefficient differential equations. So let's get started. So from the previous video, we know the two equations. The first is the Fourier transform equation, which is given by x of j omega is equal to integral minus infinity to infinity x of t e power minus j omega t dt. Alright? And we have the inverse Fourier transform. So what is this? So x of t is nothing but 1 over 2 pi integral minus infinity to infinity x of j omega e power j omega t d omega. So this is integration in the frequency domain. So now let us see some interesting properties of this. So properties of Fourier transform. So this will be similar to whatever we saw for the Fourier series, but with some special cases as well. Okay. So the first property we'll see is the linearity property. So this we very well know. So if x1 of t, and also for the convention, what will we use? We'll use this convention. X of t taking the Fourier transform gives x of j omega. So this is the shorthand notation we'll use for convenience. So let's say x1 of t gives x1 of j omega and x2 of t gives x2 of j omega. Then for the Fourier transform, a x1 of t plus b x2 of t is going to give a x1 of j omega plus b x2 of j omega. So this is simple enough to prove. We already saw it for the Fourier series. If you take this x of j omega, x of t, if you replace it with a x1 of t plus b x2 of t, then you will get, since it is an integral, it is also going to be linear, and you will get the Fourier transform as this one. So quickly let us see the proof. So x1 of j omega is nothing but integral minus infinity to infinity x1 of t e power minus j omega t dt, and x2 of j omega is nothing but integral minus infinity to infinity x2 of t e power minus j omega t dt, right? Now let x of t be a x1 of t plus b x2 of t. So what will be the Fourier transform of x of t? X of j omega is nothing but integral x of t e power minus j omega t dt. Now I can substitute this, right? So I'll get a x1 of t plus b x2 of t into dt. Sorry, e power j omega t minus j omega t dt. So now if I expand the parenthesis, I'll get a integral minus infinity to infinity x1 of t e power minus j omega t dt plus b integral minus infinity to infinity x2 of t e power minus j omega t dt. And we know this is nothing but x1 of j omega and this is x2 of j omega. So x of j omega is nothing but a x1 of j omega plus b x2 of j omega. So a and b can be complex here. It doesn't really matter. Okay, so this is the linearity property. Next we'll see the time shifting property. So what happens in time shifting? If x of t has the Fourier transform x of j omega, what do you think x of t minus t naught will have? So in the Fourier series, it was just a factor e power minus jk omega naught t naught, right? So here also it is similar. Since here we don't have k omega naught, we just have omega. It is j omega t naught x of j omega. So only the phase changes. The magnitude is going to remain same. Again, we'll see a quick derivation. So we'll use the inverse Fourier transform. So x of t is nothing but integral minus infinity to infinity. We have 1 by 2 pi factor x of j omega e power j omega t dt, d omega, sorry, right? Now if we have x of t minus t naught, then this is nothing but we have to replace t with t minus t naught. And there is only one term here with t. So j omega t minus t naught to d omega. Now if you try to bring the right hand side to the inverse Fourier transform form, we have x of j omega e power minus j omega t naught into e power j omega t d omega. So this is like the Fourier transform of x of t minus t naught, right? So if we call this as x1 of t, this is nothing but 1 by 2 pi integral minus infinity to infinity x1 of j omega e power j omega t d omega. So x1 of j omega is nothing but x of j omega into e power minus j omega t naught. So what is the observation here? Magnitude of x1 of j omega is equal to x of j omega, right? When we do the time shift, the magnitude doesn't change, only the phase is affected. And how is the phase affected? It is affected by a factor of omega t naught. So it varies with frequency. The phase itself is varying with frequency. And how is it varying? It is varying linearly. So phase varies linearly with frequency. Okay. So next let us see even and odd property. Odd symmetry. So what happens if x of t is even? What happens to the Fourier transform? If x of t is even, we want to find what happens to x of j omega, right? So x of t is even, meaning x of minus t is equal to x of t. So let's say x of t has the Fourier transform x of j omega. We want to find the Fourier transform of x of minus t. So x of minus t, Fourier transform we have to find. So let us first write this down. So integral minus infinity to infinity x of t e power minus j omega t dt, right? Now I want to find x1 of t equal to x of minus t. So what is the Fourier transform of that? So it is integral minus infinity to infinity x1 of t e power minus j omega t dt, but x1 of t itself is x of minus t. So this becomes minus t e power minus j omega t dt. Now I want to relate between this and this. So I can see x of t and x of minus t differs by the coefficient of t. So what I'll do, I will replace minus t with tau. So then dt becomes minus d tau, right? And the integral values becomes from infinity to minus infinity. So x of tau e power, here there is minus t, that also becomes tau. And it becomes minus d tau. But this minus we can take to invert the integrals, right? So x of tau e power j omega tau d tau. Now there is x of tau and this is x1 of j omega. So if I compare again this equation with this equation, I can see this only the e power j omega tau term is differing. So what I'll do, I'll just replace omega with minus omega. So this is nothing but x of tau e power minus j minus omega into tau d tau. So again, then what will this become? This will become x of minus j omega. Can you see that, the relation? So for x of minus t, the Fourier transform is x of minus j omega. Right? So this we wanted to find, we found out here. So if x of t is even, we have x of t equal to x of minus t, which implies x of j omega equal to x of minus j omega. This implies x of j omega is also even. So even signal also gives a even Fourier transform. So if x of t is odd, we have x of t equal to minus x of minus t, and this implies x of j omega is equal to minus x of minus j omega. This implies x of j omega is also odd. So even signal taking Fourier transform gives a Fourier transform which is even, and vice versa for odd as well. So next property, let us see conjugation and conjugate symmetry. So for this x of t, if x of t gives x of j omega, we want to find what does x conjugate of t give us. So let us find. Okay. So initially we have x of j omega is nothing but integral minus infinity to infinity x of t e power minus j omega t dt. Now let us take conjugate symmetry on both sides. Taking conjugate on both sides, what do we have? So our goal is to find x star of t. So we want to modify this to x star of t. So we are taking conjugate. So we have x star of j omega is equal to minus infinity to infinity x star of t, and this also will change. Conjugate of e power minus j omega t is e power j omega t. And t and dt are real variables, so their conjugate will be same as dt only. Okay. So now we have this x star of t, but for Fourier transform we want minus j omega t. So what we do? We just take omega to be minus. X star of minus j omega is nothing but minus infinity to infinity x star of t e power minus j omega t dt. So this is nothing but the Fourier transform equation of x star of t, right? The conjugate of t. So x star of t Fourier transform is nothing but x star of minus j omega. So it is having a conjugate and also minus sign in the omega. So this is Fourier transform, Fourier transform. So now let us see some properties. What happens if x of t is real? So what happens if x of t is real? We have x of t is equal to x star of t. So x of j omega is equal to x star of minus j omega, right? So if it is real, and let's say x of t is also even, real and even. So what happens in that case? We have x of j omega equal to x of minus j omega, right? So we have x of j omega will be equal to x star of j omega, because x star of minus j omega is also equal to x star of j omega. So this means this is also real, right? And since we already saw in the previous property, right? So it is also going to be even. So x of j omega is real and even. So in the next case we have if x of t is real and it is also odd. If x of t is also odd. So what happens in that case? We have x star of minus j omega equal to minus x star of j omega, right? So we have x of j omega equal to minus x star of j omega. This implies it is imaginary, purely imaginary. So here also it is like purely real. I am not writing it. It is understood. So again from the previous property we saw it is also odd. So x of j omega is imaginary and odd. So in the next case what we have, if x of t is imaginary, so we have x of t equal to minus x star of t. So x of j omega is equal to minus x star of minus j omega, right? So again here if x of t is even, what do we have? X star of minus j omega is equal to x star of j omega, which implies that x of j omega is equal to minus x star of j omega. So it is going to be imaginary. So x of j omega is going to be imaginary and even. What about if x of t is odd? So then x star of minus j omega will be equal to minus x star of j omega. So your x of j omega will be equal to x star of j omega. So this implies it is real. So my x of j omega is going to be real and odd. So these are the 4 cases which we saw in the conjugate symmetry. So next property, let us look at differentiation and integration. So property number 5, differentiation. So what we have here, so if x of t gives a Fourier transform of x of j omega, what happens to dx of t by dt? What do you think from the previous thing? So in the Fourier series, it was multiplied by the factor of jk omega naught. So here it is just going to be j omega x of j omega. So let us derive this. From the inverse Fourier transform, I have x of t is 1 by 2 pi integral minus infinity to infinity x of j omega e power j omega t d omega. So my dx of t by dt, its inverse transform is going to be, so if you see we need to differentiate by d by dt, right? So if you see this is only dependent on omega, this is also only dependent on omega, so only this will get differentiated. So differentiation of e power j omega t is nothing but j omega e power j omega t d omega. So putting it in the form of inverse Fourier transform, I have j omega x of j omega e power j omega t d omega. So this is going to be my Fourier transform, right? So that is what we have here. Okay, this is for differentiation. So now let us see about integration. Integration. So for integration, again it is just reverse of differentiation. So we can say it is just 1 by j omega, but let us see what happens. So if x of t has a Fourier transform of x of j omega, then what about integral minus infinity to t x of tau d tau? Okay, so first x of tau, if we write it in the form of inverse Fourier transform, we have 1 by 2 pi integral minus infinity to infinity x of j omega e power j omega tau d omega, right? Now if we integrate x of tau d tau, So again this integral we can take inside and only this term depends on tau. So x of j omega integral minus infinity to t, e power j omega tau d tau into d omega. So this integration will actually give me 1 by j omega, right? Minus infinity to infinity x of j omega into e power j omega t, because it has become t here now, into d omega. We have by j omega factor here. So this will be the Fourier transform for me. So this is nothing but 1 by j omega x of j omega. So I get a division by the factor of j omega for the integral. But if you also see, for the integral to be valid actually, for integral minus infinity to x of tau d tau to be valid, x of t or x of tau should not have any dc term. Because if you integrate the dc term from minus infinity to t, it is going to be infinity. So which makes x of t as a whole itself going to infinity, and we know that if it is absolutely integrable, it will have a Fourier transform. So in this case, the x of tau should not have a dc term. This is also the case for Fourier series. I think we forgot to discuss it there. But even for the Fourier series, integral minus infinity to t x of tau d tau for x of tau periodic should have the dc component a naught going to 0. So then only this integral will be valid, right? Otherwise this will not converge. It will tend to infinity. So, and the other thing is, so when we integrate, there can also be the constant. So this integral itself can have a dc value, but that is not reflected here because as omega tends to 0, this is not valid, right? One thing is x of j omega is 0, so this whole term should go to 0 when we tend omega to 0. So this omega in the denominator will not actually affect it, but also this after the integration it can have a dc term, right? So that dc term is given by pi x of 0 delta of omega. So this will represent the dc term after the integration. So this is actually coming because this integral is not a simple integral, but it is a complex integral. You can see it is e power j omega tau. So if you know the theory of complex numbers, you can actually try to do this integral and you will get this extra term also, pi of delta of omega. So that is where this is coming from. And if you see here, by dc term I mean if it is a constant signal, right? This constant signal, then that integral will be diverging, it will go to infinity. But this x of 0 is nothing but integral minus infinity to infinity x of t dt. So this is supposed to be finite anyways, right? So this can have a finite value. And this term diverges at omega equal to 0. So you need to, this is not valid for omega equal to 0. You need to consider this for omega equal to 0. So next let us see the time and frequency scaling. So it is property number 7. So these time and frequency scaling are related. So if x of t gives a Fourier transform, x of j omega, what does x of at give? So let us try to find out. So we have x of at, right? The Fourier transform. Let's say x1 of t is equal to x of at. So x1 of j omega is nothing but integral minus infinity to infinity x1 of t e power minus j omega t dt. So So this is going to be integral minus infinity to infinity x of at e power minus j omega t dt, right? And if I replace at with tau, then I have dt is equal to d tau by a, right? And the integrals also will vary according to the sign of a, right? So the sign of a also matters. So if a is positive, so d tau by dA, a is positive, and limits remain same, correct? And if a is negative, d tau by a is negative, and limits change like inverse sign, but we can again invert it back with the negative sign of d tau by a. So we can just write this as mod a, right? And limits minus infinity to infinity. So I have x1 of j omega is nothing but integral minus infinity to infinity x of tau e power minus j omega, t becomes tau by a d tau by mod a, right? And the limits remain same. So this way I can write it. So and what do I have here? So I have 1 by mod a integral minus infinity to infinity x of tau e power minus j omega by a tau. I can take this a as a coefficient of omega d tau. But if you observe this term, this is nothing but x of j omega by a, right? It is the Fourier transform of x of t with omega replaced by omega by a. So this is nothing but 1 by mod a x of j omega by a. So this will be the Fourier transform of x of at. So x of at as the Fourier transform 1 by mod a x of j omega by a. So what you can observe here, the Fourier transform is decreased in frequency by a, right? So it is having a scaling in the amplitude and also in the frequency. So if t is multiplied with a, omega is going to be divided by a. So this you can also understand from the inverse relation between the time and frequency. So this seems possible. So from here only you can derive what happens to the time reversal. So x of minus t is going to give you, a is minus 1 here, so it will just be x of minus j omega. So this is what we derived earlier in the even and odd property. So next we are going to see the most important property of duality. So it is property 8, duality. So let us take a look at the Fourier transform equation and the inverse Fourier transform equation. X of t e power minus j omega t dt, and x of t is nothing but 1 by 2 pi integral minus infinity to infinity x of j omega e power j omega t d omega. So if you see here, both are actually taking a reverse role, right? Here there is x of t and here there is x of j omega. On the left hand side, here there is x of j omega, here there is x of t. And we have one minus sign difference between e power j omega t and e power minus j omega t. And the coefficient is dt here, here it is d omega. And we have this 1 by 2 pi difference. So there is not much difference in deriving x of t from x of j omega, or if we are given x of t and asked to find x of j omega, again we are going to integrate using e power j omega t or e power minus j omega t as required by the equation, right? So let us try to relate or explore the symmetry between these two using an example. So it is our familiar example only. So if we have x of t as 1 for mod t less than t1 and 0 for mod t greater than t1, its Fourier transform, we know this, we already derived it many times. This x1 of j omega, x of j omega is nothing but 2 sine omega t1 by omega. Now if we have x of j omega as, or some x dash of j omega as 1 for mod omega less than capital W, let's say, and 0 for mod omega greater than W, its inverse Fourier transform, I'll call it IFT. What is it going to be? X of t. We'll find out. So we can use this equation. So x of t is, or this is x prime of t, 1 by 2 pi integral minus infinity to infinity x prime of j omega e power j omega t d omega. Right? And we have integral minus infinity to infinity. This is going to be 1 from minus w to plus w. So the integral will change from minus w to plus w e power j omega t d omega. And this is nothing but e power j omega t by jt minus w to plus w. And this is going to be 1 by 2 pi jt e power jwt minus e power minus jwt. And this one with 2j, we know it is sine of wt by pi t. So this is going to be sine wt by pi t. So you can see the relation between these two. So if I write this as sine into t into w by 2 pi into t, and I will take this 2 pi common out, I have 2 sine tw by t. So you can see the relation between this and this. So it is just replacing t with omega, right? That there is that replacement, and extra factor of 1 by 2 pi is coming. So it is actually taking the same form only. So if we try to plot it, so let's say I will plot it here. This is x of t, and this gives the Fourier transform of this way, right? So this is x of j omega, this is omega, this is t, right? And these points are going to be pi by t1, it is going to go to 0 at first. Pi by t1, this is minus pi by t1. And the second signal we have on the frequency side, we have x prime of j omega as w to minus w to w, this is omega. And its inverse Fourier transform was nothing but this signal, 1 by 2 pi, right? This is 1. And if this is 2t1, this is going to be 2 omega by 2 pi, which is going to be pi by omega. So it is going to be decreased in amplitude. So this is pi by omega, sorry, omega pi pi. And this is going to be pi by omega and minus pi by omega. So you can see how it is related, right? These two signals. There is only difference in the amplitude of the signal. So if we try to write it, so x of t gives Fourier transform of x of j omega. Now if you actually take x of t, capital X of t itself as a signal and try to take its Fourier transform, right? We just take this as a signal and then try to take it as a Fourier transform, what will we expect? That is what we have to find. So first let us take this equation, the inverse Fourier transform equation, e power j omega t d omega. Now we want to find this signal such that its inverse Fourier transform is x of t. So if we just modify this right hand side such that like we get it as a Fourier transform equation, then whatever is there on the left hand side will be this equation, right? So let us try to do that. So 2 pi x of t is nothing but integral minus infinity to infinity x of j omega e power j omega t d omega. So this omega I can replace with tau, and x of j omega I can call it x of tau. This j is just a convention, right? So if I just replace omega with tau, it will be sufficient. So 2 pi x of t is nothing but integral minus infinity to infinity x of tau, this is capital X, e power j tau, right, into t d tau, correct? And I also need to change this t to minus omega such that this right hand side becomes like a Fourier transform equation. So if I do that, then I have 2 pi x of minus omega is nothing but integral minus infinity to infinity x of tau e power minus j omega tau. I'm just flipping it, d tau. So now this right hand side looks like Fourier transform equation. So we can say 2 pi x of minus omega is the Fourier transform of x of tau or x of t, right? This is capital X. So that is what we have here, we wanted here. So I'll just copy this. So this one we have it as 2 pi x of minus omega. So if I have just one relation, it is enough. I can find if x of t is then coming in the time domain signal, then I can easily find its Fourier transform. So let us see some examples. So we saw that dx by dt gave a Fourier transform of j omega x of j omega, right? Now I want to see what happens if it is jt x of t. What is it going to be, right? Let's say capital X of t. Then it is going to be 2 pi dx of minus omega by d omega. So x of minus omega will just give an extra minus n, right? So what we can infer from this is, if we take a derivative in the frequency domain or in the Fourier transform, we'll have a multiplication by t in the time domain. So this is not the actual form because this is not jt x of t. It is the Fourier transform which is changing into x of t. So we have this 2 pi extra factor. So to see what happens if we take jt x of t. So if x of t gives Fourier transform x of j omega, let me put it a little down. Then what happens if it is jt x of t? So this we have to derive, right? So we know x of j omega is nothing but, this we want to find dx of j omega by d omega. So x of j omega was nothing but integral minus infinity to infinity x of t e power minus j omega t dt. So dx of j omega by d omega will be nothing but minus infinity to infinity. D omega of this is minus jt. So minus jt x of t e power minus j omega t dt. So this is the function. So it will be minus jt x of t. Now you can see like both side like left hand side it is just x of t and right hand side it is x of j omega. So that is the difference. So that is why you're not getting this 2 pi factor here. Because these are like entirely different functions, right? Similarly, we have the time shifting property. X of t minus t naught was giving us e power minus j omega t naught x of j omega. So we want to see what happens if it is x of j into omega minus omega naught. So it is like the frequency shifting. What happens when we shift the frequency? So we also expect to get some phase factor in the time domain. So let us see. Again, x of j omega is nothing but x of t e power minus j omega t dt. So x of j into omega minus omega naught is integral minus infinity to infinity x of t e power minus j into omega minus omega naught t dt. So we can take this term e power j omega naught t, e power j omega naught t x of t into e power minus j omega t dt. So this is the time domain counterpart. So this will be e power j omega naught t x of t, right? Similarly, we can also do it for the integral in the frequency domain, right? So we have minus infinity to t x of t dt is nothing but, what did we get? 1 by j omega x of j omega plus pi x of 0 delta omega, right? Now if we have integral in the frequency domain, j omega d omega, right? This is again omega. So I'll take another variable here, eta, let's say. Okay, and this is omega. So what will I have here? So it is going to be minus 1 by jt x of t plus pi x of 0 delta of t. Again, this one you can directly derive, but this factor again comes from the complex integration. Okay. So this is with the duality property. So next let us see the Parseval's relation. So that will be property number 9. Parseval's relation. Again, what did we say it for the Fourier series? The total energy in the time component is equal to the total energy in the frequency component. It was actually the summation of the each energy in the each frequency component or each harmonics, right? So here again it is the energy in the time domain, energy of the signal is nothing but 1 over 2 pi integral minus infinity to infinity mod x of j omega whole square d omega. It is again with the 1 over 2 pi factor, the total energy in the frequency domain. So let us derive it. So let's start with the left hand side. We have mod x of t whole square dt, and this we can write it as x of t into x conjugate of t dt, and x conjugate of t in terms of the inverse Fourier transform, we have 1 by 2 pi integral minus infinity to infinity x star of j omega e power minus j omega t d omega, right? So if we substitute that here, we have x of t whole square dt is equal to integral t equal to minus infinity to infinity x of t integral omega equal to minus infinity to infinity, and we also have 1 by 2 pi. So let me put it here, x star of j omega e power minus j omega t d omega into dt. So now what I will do, I will first integrate with respect to t and then integrate with respect to omega. So then what I have, omega equal to minus infinity to infinity, 1 over 2 pi, I can take it common out, x star of j omega because it is only dependent on omega, I am taking it outside. And t equal to minus infinity to infinity x of t e power minus j omega t dt into d omega. But this is nothing but x of j omega, right? So this is nothing but 1 over 2 pi integral omega equal to minus infinity to infinity x star of j omega x of j omega d omega. So now this is nothing but the absolute of x of j omega square d omega. So this is the Parseval's relation we wanted. So this is the derivation. So this left hand side is nothing but the total energy of the signal. And this x of j omega mod square by 2 pi is the energy per unit frequency, because the total energy is got by summing it over all the frequencies, right? So it is also called as the energy density spectrum. Energy density spectrum. Okay. So this is with all of the basic properties. So next let us move on to the special property and the most important of convolution and the multiplication. So let us see about the convolution property first. So for an LTI system, we saw that if x of t is an input, then output y of t is given by convolution of x of t with h of t, where h of t is the impulse response. Impulse response of the system, right? And also we saw that for an LTI system, if the input is e power st, complex exponential, then the output is nothing but some h of s into e power st. And what was this h of s? It was nothing but integral minus infinity to infinity h of t e power minus st dt, right? And for the Fourier series, we saw this was h of jk omega naught, again which was nothing but h of t e power minus jk omega naught t dt. Now for this Fourier transform, we have h of j omega, so which is nothing but h of t e power minus j omega t dt. So this is exactly like the Fourier transform of h of t, right? So it is also called as the frequency response. This we already saw. So now let us see what happens to the convolution property, the Fourier transform. So we know y of t given by x of t convolved with h of t is nothing but integral minus infinity to infinity x of tau h of t minus tau d tau, right? Now if we take the Fourier transform of y of t, it is going to be minus infinity to infinity y of t e power minus j omega t dt. Now let us substitute this in y of t. Again this integral is t for t, right? And we have inside integral for tau, x of tau h of t minus tau d tau into e power minus j omega t dt. So now let us first change the order of integration. Let us integrate t first, then tau. So tau equal to minus infinity to infinity x of tau, right? And we have integral t equal to minus infinity to infinity h of t minus tau e power minus j omega t dt and d tau, correct? So now let us try to evaluate this integral. So this is nothing but time shift, right? Time shifting property we can use, and what do we get? We get e power minus j omega tau h of j omega, right? So this is nothing but tau equal to minus infinity to infinity x of tau e power minus j omega tau h of j omega d tau. So h of j omega does not depend on tau, so we can take it outside the integral. So we have h of j omega tau equal to minus infinity to infinity x of tau e power minus j omega tau d tau. This is again nothing but your Fourier transform of x of tau, x of t, which is x of j omega. So I get h of j omega into x of j omega. So y of j omega is this. So what does the convolution property transform into? It transforms into multiplication in the frequency domain, right? So this is a very important property, because if we have some cascade of systems, so LTI1, LTI2, and it has impulse response H1, H2, and so on, your output LTI n, Hn, your output y of t, and input x of t. So output y of t is nothing but x of t convolved with h1 of t convolved with h2 of t convolved with hn of t. So we all know that convolution is difficult because we have to integrate it, right? And we have to integrate it region by region. It is very difficult. So, or in the other words, we can find the frequency transforms for all the systems, and it is just a multiplication, right, in the frequency domain. So which is simpler. Multiplication is always simpler than convolution. So once I have found y of j omega, then I will take an inverse Fourier transform to find y of t. So this is like a convenient way than going to do the convolution, right? So this is a very useful property. Next, we'll see the duality property of this, which is nothing but the multiplication property. So by duality, here we have convolution in the time domain. So we had multiplication in the frequency domain, right? If we add the opposite, if we add multiplication in the time domain, then by duality we can expect convolution in the frequency domain. Yes, that's right. So if I have two signals, let's say S of t having Fourier transform x of j omega, and P of t having Fourier transform P of j omega, then the multiplication, I should expect something of the form x of j omega convolved with P of j omega. Something of this sort, right? Not exactly, maybe. So let us go ahead and try to find what it is. So we have, let's call it some r of j omega, right? So r of j omega is nothing but integral minus infinity to infinity s of t p of t e power minus j omega t dt, right? So now s of t, I can write it in terms of the inverse Fourier transform relation. So let's take s of j theta. Since omega is already there, I am writing in terms of another variable theta. So e power j theta t, or j theta t, because it is s of t into d theta. So now if I substitute this here, I get 1 over 2 pi. Again, this integral is with respect to t, and this integral is with respect to theta. E power j theta t d theta into p of t e power minus j omega t dt. Now let us again change the order of integral. So I have 1 over 2 pi, which is a constant, so I am taking it outside. Theta equal to minus infinity to infinity s of j theta, because it is not depending on t, and I'll put all the depending on t variables inside. which is P of t e power j theta t e power minus j omega t dt into d theta. So now let us simplify this. Theta equal to minus infinity to infinity s of j theta integral t equal to minus infinity to infinity p of t e power minus j, this is omega minus theta into t dt into d theta. So if I see this, this is nothing but p of j into omega minus theta, right? That is the Fourier transform of p of t shifted by theta. So I can write this as theta equal to minus infinity to infinity s of j theta p of j into omega minus theta into d theta. So this is my r of j omega. But this is nothing but 1 over 2 pi s of j omega convolved with p of j omega, right? It is just a convolution in the frequency domain. So it is as expected, but we also have this 1 over 2 pi factor. So s of t into p of t will have a Fourier transform given by 1 over 2 pi s of j omega convolved with p of j omega. So this is our relation. Again, if you see, this multiplication is nothing but amplitude modulation. So you have something called as a carrier signal, and we have what we want to send, which is called as a message signal, and we modulate the the amplitude of the carrier using the message signal. So this is called as amplitude modulation, and because of this property, this entire property is also called as the modulation property. So again, this is also an important relation. Because we often encounter this kind of multiplication in the time domain. So this brings us to the end of the properties of the Fourier transforms. So now let us see some of the basic Fourier transform pairs. Again, with respect to the properties, you actually needn't memorize anything, because everything can be derived from this basic equation, right? The Fourier transform equation and the inverse Fourier transform equation. So once you try to derive it from them, like even when you're practicing problems, don't just look at the equations directly. Try to derive them from the original, those two equations. And then as you derive many times, you will actually get used to it. And then you will automatically start to remember. And in the long term, even if you forget, it's not a problem for you, because you know how to derive it again from the basic equations. So there is no need to memorize everything on the go. Okay. Now let us see some basic Fourier transform pairs. So I will write the signals here and their Fourier transform here. Again, the first one we will see is with respect to the periodic signals given by the complex exponentials. So we already saw the Fourier transform pair for this, which is nothing but 2 pi integral k equal to minus infinity to infinity ak delta of omega minus k omega naught, right? And what about for the single complex exponential? It is nothing but 2 pi delta of omega minus omega naught, because there is only that omega naught term coming here, right? So what about cos omega naught t? So cos omega naught t will be having two terms, right? E power j omega naught t and e power minus j omega naught t, and they will have a coefficient of 1 by 2. So this is nothing but pi into delta of omega minus omega naught plus delta of omega plus omega naught, right? And what about sine omega naught t? This is again the same, but we have 1 over 2j and also a minus sign. So pi by j into delta of omega minus omega naught minus delta of omega plus omega naught. Okay. And for x of x of t equal to delta of t, we had the Fourier transform as 1. But what happens if it is the other way around? If it is 1, then we know using duality, this is going to be 2 pi into x of minus omega. So delta of minus omega, which is nothing but 2 pi delta of omega. Because it is an even signal, delta of minus omega is going to be equal to delta of omega. So for even signals, I'll write it here. For even signals, x of t gives x of omega, j omega, and x of t is going to give 2 pi x of omega. So there is no minus here. For other signals, it is actually minus, but for even signals, x of minus omega is going to be equal to x of omega. So they just differ by a factor of 2 pi. Okay. And for the periodic square wave, what do we have? X of t equal to, sorry, not periodic. Okay, let's see the periodic square wave first. So we have mod t less than t1, 0 for t1 less than mod t less than or equal to t by 2, and periodic with t. So for this, what was the Fourier transform? The Fourier series coefficients were sin k omega naught t1 by k pi, right? So a case where sin k omega naught t1 by k pi, or now for the Fourier transform, what will we have? It is 2 pi into ak summation ak delta of omega minus k omega naught. So it is actually summation k equal to minus infinity to infinity. Pi cancels, so we have only 2 left. 2 sin k omega naught t1 by k delta of omega minus k omega naught. So this will be the Fourier transform. And for the non-periodic square wave, what do we have? X of t equal to 1 for mod t less than t1, 0 mod t greater than t1. So for this, it was just 2 sin omega t1 by omega, right? And then we also saw for the periodic impulse. So if it is k equal to minus infinity to infinity, delta of t minus kt. So this is again periodic. So its Fourier series coefficients were 1 by t for all k. So its Fourier transform is going to be 2 pi by t summation k equal to minus infinity to infinity delta of omega minus k omega naught. And what is omega naught here? 2 pi by t. Okay. So then what do we have? So again, this duality we have sine of wt by t or pi t. Sine of wt by pi t. It was nothing but x of j omega equal to 1 for mod omega less than w and 0 for mod omega greater than w. Okay. And u of t we actually did not derive, right? So let me derive it here. So u of t. So u of t is nothing but, so delta of t gave 1 and u of t is nothing but integral minus infinity to t delta of t. So this should give me 1 by j omega plus pi into x of 0 delta of omega. So x of 0 is again 1. It is because it is 1 for all omegas. So this is equal to 1 by j omega plus pi delta of omega. So this is the Fourier transform of u of t. It's 1 by j omega plus pi delta of omega. So this one you can also find, this pi delta of omega is nothing but, so 2 pi delta of omega was 1. So pi delta of omega has a DC value of half. which is nothing but the average value of u of t. So from that also you can find this DC component in the frequency domain. Okay, so next we have the time shifted impulse. So this is again simple, right? This is e power minus j omega omega t naught. From the time shifting property, we know this. And then we also had e power minus at u of t, and a is greater than 0. So for this, we had 1 by a plus j omega. We actually derived this. We had it as 1 by a plus j omega. And suppose we wanted to find t e power minus at u of t. So this is nothing but minus d by dA of this term. So I'll write it here. E power minus at u of t was giving 1 by a plus j omega, right? So in other words, we can also write it as 1 by at u of t is nothing but 1 by 2 pi integral minus infinity to infinity 1 by a plus j omega e power j omega t d omega. So if I take d by dA minus d by dA on both sides, this side, left hand side, I'll get t e power minus at u of t 1 by 2 pi integral minus infinity to infinity. Right hand side, only this depends on a. So if I take derivative, I'll get minus 1 by a plus j omega whole square. But minus sign cancels, so I'll get 1 by a plus j omega whole square e power j omega t d omega. So this is my Fourier transform. So this is 1 by a plus j omega whole square. So if I take another derivative, what will I get? I'll get t square. So again minus d by dA. I'll get t square e power minus at u of t. And on the right hand side, I'll get 2 by a plus j omega whole cube e power j omega t d omega. So for t square e power minus at u of t, it is, and let me push this little up, it is 2 by a plus j omega whole cube. So for t power n e power minus at u of t, what do you think it will be? So it will be n factorial by a plus j omega whole power n plus 1. Okay. So these are our basic Fourier transform pairs. So we can use this in combination with the properties to find many other Fourier transform pairs as well. For example, if you want to find cos omega t plus sin omega t, you just add them, right? And if you even want to find cos 2 omega t, you just do the time scaling property. So this is where these properties are all helpful, right? You needn't go again and derive it from the basic equation, the Fourier transform equation, again do the integral. That is not required. You can just use the property, and if you already know few of the Fourier transforms, you can use the property on them and directly get your answers. Okay, now let us move ahead to the linear constant coefficient differential equations. So LTI systems represented by linear constant coefficient differential equation. So we want to find the frequency response, which is nothing but h of j omega of such systems. So these systems are usually of this form: ak dk y of t by dtk, right? And on the right hand side we have some k equal to 0 to m bk dk x of t by dtk, right? They are usually of this form, and we know like this translates to the Fourier transform, and we want to find h of j omega of this. But from the convolution property, we know y of j omega, the output is related to the input by h of j omega in this manner. So we can find h of j omega by actually taking the ratio of y of j omega and x of j omega. And we know this differentiation is related directly to the Fourier transform. So dy of t by dt is nothing but j omega y of j omega. So k is nothing but, you will get a factor of k here. So this again you can represent it as summation k equal to 0 to n ak j omega whole power k y of j omega is equal to summation k equal to 0 to m bk j omega power k x of j omega. So now this y of j omega is actually common, so I can take it out. Y of j omega into summation k equal to 0 to n ak j omega k is equal to x of j omega into summation k equal to 0 to m bk j omega k. So y of j omega by x of j omega, which is nothing but my h of j omega, is nothing but summation k equal to 0 to m bk into j omega power k by summation k equal to 0 to n ak j omega power k. This is my frequency response of the linear constant coefficient differential equation. So let us see one example. So example. Let us take this differential equation. So what will mean by b my h of j omega? It will be 1 by j omega plus a. This is nothing but 1 by a plus j omega. So this I already know, right? So this is nothing but h of t is nothing but e power minus at u of t for a greater than 0. So this way I will be easily able to find my impulse response also. And for, let's say for a given input, if x of j omega is a plus j omega, then my y of j omega is going to be 1, and which is taking inverse Fourier transform, it is going to be delta of t. So if I know that x of j omega is a plus j omega, to find y of t from this equation, I have to do many things. But if you see, if I take this frequency domain path, it is very easy for me to find y of t. So this shows the power of the Fourier transform. So that's it for today. I think it's a long class. I have covered many things. Please go back and revise. And in the next class, let us solve some problems. Until then, take care. Bye.